For there to be a force in space related to charged particles, there physically has to be two charged particles. They have to act on one another. And it could be two protons, which would repulse. It could be two electrons, which would repulse. It could be a proton and an electron, which would attract. But the point is that there always has to be two of them. So how do we describe the situation in space if there's only one particle? What if I've just got a little lonely proton sitting out there all by his lonesome? What do I do? Well, instead of using the concept of force, I'm going to use the concept of electric field intensity. And the electric field is a description of how a single charge or a collection of charges, it doesn't have to be just one, but it's a description of how these charges are going to influence the space they occupy. And what you may think of is, well, what would happen if I put a charge in here? There isn't one, but what would happen if it was near here, if I put a little charge at this location, for example? For example, suppose I fix this charge, I call it Q1 here, and I fix him at the origin in Cartesian space. I put him right in the middle of the XYZ grid. We could calculate the force that acts on any charge placed near Q1. I could put it in space. I could calculate the force acting on that. And in fact, I could calculate the force vector that acts on some test charge at any point in space. It could be here, it could be down here, it could be here, it could be right next to it, you know. And this is the concept of a field. We want to know how strong the force would be as a function of position around that charge. How strong the force is dependent on how much charge is present here at Q1. And so we therefore define this concept of electric field intensity, which is the force generated per unit charge. And that is the electric field intensity, E, is equal to the force that would be generated on a test charge divided by the magnitude of that test charge. So this is Coulomb's law right here. We just divide Coulomb's law by Q2. And so what this is it's Q1 over 4 pi epsilon times the magnitude of the radius away from the charge, and we give it what's called the radial unit vector. This is a new thing. So what is the radial unit vector? If I have a test charge here, the notation radial unit vector just means that it's getting pushed away radially. If I have a test charge here, it's getting pushed away radially. So we're just saying that this thing, there's always a straight line drawn from here to here, acting as if there was a circle of charge, electric field surrounding this charge that pushed these guys away in a straight line. That's what that means. Although it's not immediately obvious, the units of the electric field intensity are volts per meter. I'm not going to bore you with the details of deriving that, but not the total derivation at least. I'm just going to do a simple one. The electric field is going to be coulombs. 4 pi is unitless. We know that epsilon is farads per meter. We've got meters squared here. Oh, I left off a squared term, right? Meter squared term. And so that's equal to coulombs per farad meters. And if you remember your basic definitions from fundamentals courses, 1 farad is 1 coulomb per 1 volt. And so what we've got is coulombs per coulomb volts times meters. Your coulombs cancels, volts goes to the numerator, and you end up with the fundamental units of electric field as volts per meter. So little derivation there based on fundamental units. So to reinforce the concept of E field intensity, I want to perform an example. And in this case, we've got a charge, a 10 nanocoulomb charge located at 5 meters along the x-axis. We want to place another 1 nanocoulomb point charge someplace in space and we want the total electric field intensity measured at the origin to be 0 volts per meter. So if we were to visualize that, what we've got is we take space, we turn it into a Cartesian system, and there is a charge 1, 2, 3, 4, 5 right here, and we're measuring electric field intensity at the origin. And this guy here is a 10 nanocoulomb charge, and what we have is we've got a 1 nanocoulomb charge that we have to place someplace around here. And I think it makes intuitive sense that to cancel the effects of this charge at the origin, we're going to place a charge someplace along the negative x-axis. And since this is 10 nanocoulombs and our test charge is 1 nanocoulomb, it's going to have to be closer to the origin than this one is. And so our real problem that we have to solve here is, well, how close to the origin? And so again, I'm using that concept of qualitative instead of quantitative analysis here before I even start, just to kind of make sure that I understand the parameters of the equation that I'm asking. So quantitatively, what we want to do is we want to write the equation for the electric field at the origin due to this 10 nanocoulomb charge, and that is equal to Q over 4 pi epsilon, magnitude of the radial distance to where we measure the electric field intensity at, squared, and it's the vector points radially. So A hat R, remember, is our notation for that. So we need this R, and we'll just call it R1 in this case, indicating that it's from Q1. So R1, remember, it is the vector pointing from here to here. So that's equal to 0 minus 5, which is the x position of this charge, A hat x, and then all other components of that vector are going to be 0. So it's just equal to minus 5 A hat x. The magnitude of R1, finding that's trivial, it's just equal to 5. And so therefore, the vector pointing radially is, the unit vector pointing radially is just R1 over the magnitude of R1, which is just minus 5 A hat x over 5 is equal to minus A hat x. The unit vector is pointing in that direction. So what that's saying is the E field due to this charge points in the negative x direction. So we can solve this equation. E1 vector is equal to the charge, the magnitude of the charge, which is 10 times 10 to the minus 9th coulombs over 4 pi times 8.854 times 10 to the minus 9. Then we need to multiply it by the magnitude of the vector squared. And then that points in the minus A hat x direction. So we get, if we were to write this, to be exact, I'm going to say that that equals minus 10 nanocoulombs over 25 times 4 pi, which is just 100 pi times epsilon 0 in the A hat x direction. So that way I'm not doing a lot of rounding. So our second charge has to cancel this. And so what we say is that E2 has to equal 10 nanocoulombs over 10 pi epsilon 0 A hat x. It has to be equal in magnitude but opposite in direction to cancel. So we look at that, we see that the A hat R2 only has an x component, just like A hat R1, or the unit vector pointing from here to here is only in the x direction, and the unit vector pointing from here to here is only in the x direction, and that makes kind of intuitive sense. So to solve this, we just set the electric field intensity equation, Q2 over 4 pi epsilon 0 magnitude of R2 squared A hat R, that's going to be equal to 10 nanocoulombs over 10 pi epsilon 0 A hat x. So I set the general formula for electric field strength equal to the specific value that we calculated that's necessary for this problem. That's not Q squared, that's Q2. Sorry about that, Q2. So we know that the value of Q2, that's the charge we're going to insert, it's 1 nanocoulomb. So 1 nanocoulomb over 4 pi epsilon 0 times the magnitude of R2 squared, the unit vector pointing radially, is equal to 10 nanocoulombs over 100. Guys, I've been writing 10 pi, that's 100 pi. If you carry that out down there, I made a mistake there, that's 100 pi, not 10 pi. So this denominator over here is 100 pi epsilon 0 A hat x. So what we need to do is we need to just solve for R2 here, and so we can just do that by multiplying or dividing both sides by this quantity right here. So 1 over the magnitude of R2 squared times A hat R is equal to 10 nanocoulombs over 100 pi epsilon 0 times 4 pi epsilon 0 divided by 1 nanocoulomb in the A hat x direction. And so if we were to solve this, we would see that R2 is equal to 1.58 A hat x. So R2 A hat R, kind of the R2 pointing in the A hat R direction, is 1.58 A hat x. So the solution to this is that we actually want to put this 1 nanocoulomb test charge 1.58 in the negative direction there. It's 1 nanocoulomb, so that's 1.58 meters. And then the two charges will cancel one another out. And so the final answer is Q2 is located at minus 1.58 in the x direction, 0 in the y direction, and 0 in the z direction.